So let us go for the next topic in queuing models, that is queuing notation. So how to represent a parallel server queues. So to represent this, there is a notation here. So that is A/B/C/N/K. So what is A here? A represents the inter-arrival time distribution, whereas B is going to represent service time distribution and C is going to represent number of parallel servers. So here N also represents the system capacity and K represents the size of calling population. So you know what is size of the calling population means. It is, we generally take the number of customers here. Okay, it is called size of the calling population. And here the system capacity can be finite or infinite. Again, the calling population also can be finite or infinite. So suppose I take an example here to represent a particular server queue. So that is example here I am taking it as m/m/1/infinity. So here, before going for this example, see, there is one more representation. So instead of writing here A/B/C, so instead of writing A here, I can replace this A by one more term, that is M. Okay, or sometimes D also can be represented, and also sometimes G also can be represented. You are going to replace this A by M or D or G sometimes. Okay, so what if you represent M, that means it is following the Poisson distribution. And D, if you are going to represent instead of A here, if you are going to represent D, it means the deterministic distribution. If you are going to represent G there, if it represents the general distribution. Similarly, instead of writing B here, you also can represent M or D or G. Okay, so C represents your number of servers. Okay, for example, I am going to write the notation here m/m/1/infinity/infinity. So m represents now the Markov's distribution or exponential distribution. Okay, and 1, if you are going to write there, /1 you have. 1 means the number of server is equal to 1. So that is only one server is going to serve the customers. Okay, so that is one kind of representation. Okay, the same notation can be represented in another form, that is instead I remove this infinity/infinity and I just write m/m/1. So both are same. If you are going to represent m/m/1/infinity/infinity, or sometimes you can represent it as m/m/1. Both are same. Okay, so don't confuse. You can in the short form you can write m/m/1. So this is one example. This is showing a simple system. For example, if you are considering customer service desk in any store, so in that particular system, the number of customers may be any kind. Okay, you cannot predict it, so we consider it as infinity. But one server will be there. In one store, we'll be having one shopkeeper. So there the number of server is only 1. So another example, if you are taking m/m/C. Okay, so this C can be equal to 2, or sometimes it can be equal to 3 or 10, depending on the condition. Okay, so now it is going, if it is more than 1, it is going to represent the multiple server. For example, if you are considering where you have multiple server systems in the airline ticket counters or reservation counters, so there the number of servers may be multiple. Okay, you cannot have only one counter in an airline ticket counter or reservation counter. It should be always more than 1. So that is m/m/C. C value can be more than 1. So next representation is m/d/c. So now this is deterministic. distribution. That means a constant service is being provided here. So for example, you can take there for m/d/1, you can take the example of automated car wash. So there is constant service. The server is one, but it is the distribution is a constant or deterministic, you say. Okay. So next one example is m/g/1. So any general service shop or any repair shop example you can take for m/g/1. And next we have m/s/(n). So n represents here the size of the colleague population. So n can be equal to 8 or 10 or 15. So there is limited population here. Okay. So in that system you can represent m/s/(infinity). The system capacity is infinity, but slash capital N. So n can be a size of the calling population, so that is, it can be many, but it is limited. Okay, it may be fixed there, 100 or 8 or 10, like that, the numbers. So the next notation here, actually to measure the performance of the queuing system, we denote so many symbols here. So then go through these notations. So first notation is Pn. Pn represents the steady state probability of having n customers in the system. Pn of t represents the probability of having n customers in the system at time t. Lambda represents arrival rate. Lambda e represents effective arrival rate. Mu represents service rate of the one server. Rho represents server utilization. An represents inter-arrival time between customer n-1 and n. For example, it may be represented as in the problems it may be represented as A1, A2, A3, A4. Okay, the first customer arrives at 0, second customer arrives at time 5, like that. Okay, so but inter-arrival time is, you have to subtract that particular values. So it may be you know that, is it inter-arrival time between customer n-1 and n. So next is Sn. Sn represents the service time of nth arrival customer. For example, it can be represented as S1, S2, S3, so on. And Wn represents total time spent in the system by the nth arriving customer. Wn raised to q represents total time spent in the queue by the customer n. Lt represents the number of customers in the system at time t. So remember that Lt is going to represent the number of customers in the system at time t. Okay, it may be at time 5 minutes, the number of customers in the system may be 1. If the first customer goes back and there is zero number of customers in the system, again the third customer arrives, again the number of customers in the system may be 1. So it may be increasing or decreasing depending on the problem. Okay, so next is LQ of t, the number of customers in the queue at time t. L represents long run average time number of customers in the system. Next, LQ represents average time number of customers in the queue. Next, W represents long run average time spent in the system per customer. WQ represents long run average time spent in the queue per customer.